Okay, this is an answer key for potential energy diagrams in physics. We have potential energy on the y-axis, and on the x-axis, we have displacement. At position A, we have equilibrium because the slope of this is 0, but we have a neutral equilibrium since moving it to the left or to the right causes very little change. At position B, again, slope is 0, but we have an unstable equilibrium since moving it to the right or to the left will cause drastic changes. Position C, again, is an equilibrium, but here it is a stable equilibrium because if I move it to the right or to the left a little bit, it will come back to the original position. So that's why it's called a stable equilibrium. And again, we have a neutral equilibrium at position D. It's like a flat zone in our potential energy. And then at position E, another unstable equilibrium at position E. So it's moving to the right to the left would cause drastic changes in it. So that pretty much answers our questions here. The positions of neutral equilibrium are A and D. Okay, stable equilibrium is C, and unstable equilibrium are B and E. At which position are the net forces equal to 0? That would be all of them because they all have a slope of 0. Now what if I look at the forces involved with this? Well, again, the force is the slope, but it's also the negative slope of a potential energy graph. Okay, so the question is at what positions is a net force equal to 0? Again, that's all of our equilibrium positions. But what about between what positions is net force positive? When we look at our graph then, at these positions from B to C, those are negative slopes. So the force there is going to be positive because the negative slope of a potential energy graph equals force. And then after E, all of these are negative slopes, but we have to take the negative of that to make those positive. So where is the force actually negative? Between positions A and B, we have a positive slope here. From C to D, a positive slope, and D to E are positive slopes. But the force is the negative of that. Okay, therefore, our sloping positive forces are actually negative. Now, what if we release this object from position E and have it travel in the negative x direction? Through what positions can it actually go through? Well, E has a certain amount of total energy. The total energy here being gravitational or some kind of potential energy. If it's released from rest here, it can travel through D, it can travel through E, C, but it does not have enough energy to get back up to B. So that means it can travel through positions D and C, and then it'll travel up to about right here, equal and the same height. Then, of course, it will go back downwards and come back up, and it'll oscillate back and forth between these two, assuming that there is no non-conservative forces. Now let's put this into our practical applications then. We have this potential energy diagram here, varying from 6 joules around all the way to it looks like about 4 joules. First question then, estimate the force acting on the object at position 2.5. Well, then what I'll do is I'll draw in a tangent line at that position. I'll pick 2 points on that tangent line and take the slope of that. I'll take the opposite of that because force is the opposite sign of our slope. So for this example, I calculated a slope value of 4. I made that a negative 4 then. So then about negative 4 newtons, and that's just an estimation. What is the acceleration of the object at 2.5 meters? Well, we know that net force does equal mass times acceleration. So my acceleration will be my force divided by the mass. The mass is 0.125 kilograms. Therefore, I'm getting negative 32 meters per second squares. Now, what if my object starts from rest at 1 meter? Well, I go up here. That has 5 joules of energy. What would its velocity be at 2 meters? Well, I go at 2 meters, I see that we have 0 for its potential energy. So I know that the negative change in potential energy must go into kinetic energy. So I'll take 0 minus 5, and that'll give me a negative 5 joules. but an opposite of that makes it 5, and I'll set that equal to 1/2 the mass times velocity squared. I just got 8.94 for that. Now what if we start from rest at 1 meter? We want to calculate the velocity at 3 meters. Well, my final potential energy there is 3 joules. So I'll take 3 minus 5, and that gives me a negative 2 joules. But I need to take the negative of that to give me a positive 2 joules. And I set that equal to 1/2 mass times velocity squared, because the negative change in potential energy is going into kinetic energy. That gives me 5.66 meters per second. Now what if my object starts from rest at 1.5 meters? What is the maximum displacement that the object can have? Okay, so here I go. My maximum displacement, I'm starting at 1.5 meters, which is about 2 joules of energy, and I will oscillate back and forth, okay, between these two positions then. So I'll go 2 joules all the way through. So it looks like about 2.6 meters would be my maximum displacement there as it oscillates back and forth, because I can't go greater than 2 joules. So I can go down here and then climb back up. So that'll be what the object does. What is the maximum velocity then that the object can have at question 5? Well, that would be where the greatest change of potential energy is. So it looks to me like that's going to be at 2 meters. Okay, so 2 meters, I'll do 0 minus 2 gives me 2. But now I have to take, that would be negative 2. So I take the opposite of that to give me 2. Set that equal to 1/2 mv squared, and I'll get 5.66 meters per second.